Hi everyone. This is going to be a quick video to talk about part 3 of Project 1, and in particular to talk about the blurring filter. And I want to give a couple of helpful suggestions on how to approach this problem. So, uh, looking at what blur does, first let me just pull up an example. So this is from a movie, The Matrix. This is Neo, one of the main characters. He's like, I forget what he's doing here, stopping the bullets or something. Uh, our blurring function is going to take any kind of given input image and make it blurry. So you can see here, go from here to here. It might be hard to see on the YouTube video. Kind of zoom in a little closer so it's more obvious. But the image just looks blurrier. And generally, the way we make an image blurrier is by making the lines that are in the image less precise. So these edges, these sharp edges where color goes from one color, very light, to very dark, we can make that blurry by making the transition less sharp, so more smooth. And so making the kind of lighter color slightly darker the closer it is to the place where the finger ends, and the darker color slightly lighter. Luckily, you don't have to think too much about this because we describe exactly how to approach blurring an image. So for each pixel at a given location, you can think of a 3x3 sliding window. So for every pixel you want to blur, you're going to update that pixel's value to be the average of all of the pixels around that image and the pixel itself, around that pixel and the pixel itself. So actually, I have some slides here. So this laughing emoji that we had from the lecture 12, just kind of pulled it up here, made it a little bigger. So we have this image made up of pixels. How do we go about making the pixels blurry? Well, I have this box I'm going to make here that's 3x3. Let's just make this transparent so we can see everything, and kind of slightly bigger and red. And so for each pixel in our image, let's say that we pick, let's say that we pick, for example, this pixel here. I'm going to draw a box around it. And this box will be perhaps a different color. Yeah, let's make this a green box. So to make that pixel average, blurry, we look at a sliding window that is 3x3. And we take all of the pixels inside of this window, including the pixel that's in green, and we average them. Actually, I'll move this over here, make this a little clearer. And what you get is that'll make this pixel right here a little bit darker than the yellow that it was before, because all the pixels around it are yellow, and this one pixel is black. And so because this pixel will get a little darker, the black pixel over here will get a little lighter when we do its blurring. The line between the pixels, the difference between light and dark, gets kind of more gradual, and that's what makes the image more blurry. So I have this here, this view. So any kind of pixel that we center it on, this tells us how to calculate the average. We add up all of these pixels inside the box, and we take their average red, green, and blue values, and we set the middle of the pixel to be that average. Now the challenge in this problem, the challenge is, okay, that makes sense for all of these different possible pixels, where, pixel number 5 here is the center, so that's the pixel that is being set to the average. The real challenge is what happens when we get to a pixel that is on the outside border. So any one of, I think this is actually easier to see if I present. So what happens when you get to any one of these pixels? So along any of the borders. Because then you'll notice if we have a sliding box, what are you supposed to do? So let's say we start in the top left, because remember, number 5 is always the pixel. This is the center of the filter. This 3x3 image is exactly what we're averaging. So here, pixels 1, 2, 3, 4, and 7 don't exist. And so to come up with the value for pixel 5, we have to average pixels 5, 6, 9, and 8, because the other pixels don't exist here. So 5, 6, 9, and 8 get added together, averaged, and that is the new value for pixel 5 in our new image. Okay, so that's one edge case. This is a good example of an edge case in our coding process that we need to handle in our code. So for all of the pixels, we can always grab the pixels above, below, to the left, or to the right of the pixel by 1 and add them up and average them. Specifically for the top left corner, we just grab the one to the right, the one below, and the one to the right and below. Okay, but what about this next pixel? What about if we move one over? And so, again, I'm going to keep this, I'm going to bring back this green box because I quite like it, actually. And I can group these together so they move together. Okay, so that's figuring out a new value for that 0, 0 pixel. Now what about for pixel 0, 1? Notice that for pixel 0, 1, it's actually a different edge case. So for pixels that are in the top row, but not the corner, just 1, 2, and 3 don't exist. So we add together 4, 5, 6, 7, 8, 9, average their R, G, and B components, and that is the new value of pixel 5. Great. And that works pretty well as we move across the image here. So for here, for everything in the top row except for this corner, except for the opposite corner. So if I move all the way to the opposite corner, now if I need to take the average of this 3x3 kind of filter view, so 1, 2, 3, 6, 9 now no longer exist, and so we have to add together 4, 5, 7, and 8. And so this is the pixel to the left, below, and diagonally to the left and down, southwest from the pixel we're averaging. And you'll notice this pattern continues all along each of the edges of the image. So everything in the top row except for the corners is one case. So 4, 5, 6, 7, 8, 9. Everything on the right is a different case. It's 1, 2, 4, 5, 7, 8, except for the corners. Everything at the bottom is its own case. So 1, 2, 3, 4, 5, 6 are added together. And everything on the left border is 2, 3, 5, 6, 8, 9 added together. And so what you get are 8 separate cases here. So you have to handle 8 separate cases. I'll just go in here. So, whoops. So the general case is for most pixels, sliding window. So the general case, we add together all 9 pixels in the sliding window. This is for any kind of regular pixel inside the image. But then we need all these different edge cases. So edge case number 1 is for the top left corner. Add pixels, average pixels. Let's see. If I move this to the top left corner, 5, 6, 8, 9. Okay, edge case number 2, top right corner, average pixels. And by pixels, when I say, when I say pixels, I'm talking about pixels here inside of our 3x3 kind of filter here, the sliding window. So here's pixels 4, 5, 7, and 8. 4, 5, 7, and 8. And notice this continues. So edge case number 3 is the bottom left corner. Edge case number 4, the bottom right corner. And then edge case number 5 is the top row minus the corners. And for the very top row, if it's not in the corners, then for any pixel up here, it is 4, 5, 6, 7, 8, 9 that we need to add together and average. And the same thing for number 6. Right edge, rightmost column. And I'll just copy these down to get the last two. Number 7 is the leftmost column, and number 8 is the bottom row. So we have all this different behavior. And there's a couple of ways you can approach this problem. One is you could implement this behavior, and I'll make this a little bigger so we can see. You could implement this where for every pixel index that you look at, you're going to check all these cases. If it happens to be the top left pixel, do something. Otherwise, if it's the top right, do something else. Otherwise, it's the bottom left, do something else. Otherwise, if it's the bottom right, do something else. Otherwise, if it's in the top row, do something. Otherwise, if it's in the right column, do something. Otherwise, if it's in the left column, do something. And otherwise, if it's in the bottom row, do something. And otherwise, it must be the general case, so we do all 9 pixels in the sliding window. But like that approach will work, but you'll probably have very long code if you do that. And so I have a slightly different suggestion on how to approach your problem. My suggestion would be this. Rather than having 8 different cases to handle, I would suggest that you approach this problem by making some helper functions. Because really, in all the cases, we always want to add all of the pixels that are valid pixels. The only problem is that when we have, when we're trying to come up with the blurred value, so the average value for a pixel that's not one of the general case pixels, just these pixels like 1, 2, 3, 4, and 7, so the pixel above, to the left, northwest, northeast, and southwest, they're just out of bounds. And so if you wrote code that tried to read those pixel values, you'd get an error back saying that it's out of bounds. And so that would be a problem. And so one way to handle this would be to create a helper function that for pixel, or is valid coordinate in our image. So given some image matrix and given a row index and a column index, you could write a function that will return true if this pixel coordinate exists in the image. Otherwise, return false. Whoops. Excuse me. So you could write some code that'll tell you, okay, for a given R index and C index, does this pixel exist in my image? So is this something that I can index into and not get an error? And then your code can become a lot simpler. You can just say, okay, so for a particular pixel, and let's say that we're looking at a pixel like, so for pixel, I'll give a good example here. So for pixel like 3, 7, so pixel at row 3 and column 7. Well, okay, you know what? I'll make it column 2. And so over here, I'll show you which pixel that is. So row 3 is going to be so this is row 0, row 1, row 2, row 3. And so we'll move this down, row 0, row 1, row 2, row 3. And then if I say column 2, so this is column 0, column 1, column 2. So we're looking at this particular pixel. So which pixels do we need to average? Well, so for pixel row 3, column 2, we would need to average the following pixels. So image matrix, let's see. Well, let's just start from the top row. So what is so if this is row 3, column 2, what is the index of this top left pixel in here? So if this is 3, this must be this is row 2, column 1. So image matrix 2, column 1. Then this next pixel is row 2, column 2. And this pixel here is row 2, column 3. Okay, going on. The next row is row 3, column 1. Row 3, column 1. Then the pixel itself, we include it in the average, so it's row 3, column 2. And finally, right here is pixel row 3, column 3. And then we have row 4, column 2. 4, column 2. Row 4, column 3. 3. And then row 4, column. Oh, sorry, this one here, number 8 was row 4. Did I do this right? Yeah, I did this wrong. So this is row 4. So row 0, 1, 2, 3, 4. And this is column 1. So row 4, column 1. Whoops. Row 4, column 2. And image matrix row 4, column 3. And this gives us all of our pixels. And you know what? Let's make this a little easier to look at. I'll just put them on their own lines. So these are all the pixels that are the neighbors of pixel 3, 2. So these are the pixels we have to average for the pixel 3, 2 to get it's at like the blurred new value. So notice the pattern here. So we have 222, 333, 444 for the row values, and then 123, 123, 123 for the column values. If you think back to your lecture, how do we generate this kind of pattern? I'll let you think about it. But notice that the sequence totally depends on whatever the row column value is. So we notice that the row starts from 1 before the current row, so 222, 333, 444, because 3 is the middle. And the column, yeah, starts from 1 before and goes until 1 after, so 1, 2, 3, 1, 2, 3, 1, 2, 3, because 2 is the middle. And so you need some way to generate the pixels, generate these pixels, these indices, to add them to this neighbors list. But what you can do is once you've generated these pairs, before adding them to your neighbors list, you can check if they're a valid coordinate. So if you had some magical way that I'll leave to you to figure out to generate numbers that correspond to the indices inside of this red box, well, you could check, okay, so all of the indices inside of this red box are valid. But if I were to move this red box over to a corner, for example, and I generated indices again, if I had some way of generating these indices that should be in this box, well, this is row 0, row 1, row 2, row 3. So the index of this pixel out here that doesn't exist would be row 2, column -1. So 2, column -1. That pixel doesn't exist, so you shouldn't add it to the neighbors list. 2 exists, 3 exists, 4. So this is row 0, 1, 2, 3, row 3, column -1. That pixel doesn't exist, so you shouldn't add it to the neighbors list. 5, 6. Same thing for this pixel 7. When you check its coordinates, you'll realize it doesn't exist, and then you shouldn't try to add it to the neighbors list. And so this way, you don't need to have individual cases for everything. For all these edge cases, you can always treat all pixels the same. For all pixels, generate the coordinates of the neighbors of that pixel and check if those coordinates are valid for every pair of coordinates. So over here, okay, pixel 1 is valid, pixel 2 is valid. Pixel 3 is going to have a coordinate of row 1, but column, let's see what column it would be. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So starting from 0, sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, I did start from 0, so 15. So pixel 3 here would be row 1, column 16. And so if you generate the pair 1, comma 16, you can check and find out that that's not a valid index because it's bigger than the width of our image, or bigger than the last index of our image, the last column index. And so you can avoid adding that pixel to the neighbors list, which is what we have in here. Okay, and so hopefully you can use this is valid coordinate idea to come up with a way somehow for each pixel coordinate, so 0, 0, 0, 1, 0, 2, etc., for each of those pixel coordinates, generate the list of all the neighbors that are valid pixels, and then average that list, because averaging a list is much easier, because we know how many pixels are in the list. Num_pixels equals the length of our neighbors. And so once you have your neighbors, you can come up with an average very easily, because you can just loop through your neighbors for pixel in neighbors, r equals 0. We can just add up r equals pixel, r equals r plus pixel 0. This could be like maybe the r total. Finally, your new r value should be r total divided by number of pixels. The very last thing I'll tell you is that for this image matrix, you can't update the value of the pixel as you go. You can't mutate your input image, because if you were to calculate a new average for this pixel right here, it's pixel number 5 there in the middle, well, when you went on to do the next pixel, it would now be pixel number 4. Your pixel, the fact that you changed the value of an existing pixel, will mess up your blurring calculation. So you're always averaging the pixels in the original image to make the new pixel. You can't use the new pixel that you created in the average for the next pixel. And so for that, you need to make an exact copy of your image. And you could write your code for this yourself, but I'll show you a quick and easy way to do that. If you want to make a blank canvas, just or an exact copy of a list that you can modify, you can import the copy module, and in your code you can use copy.deepCopy, and you can give it a thing to copy. So output image equals copy.deepCopy image matrix. And now any modifications you make to output image won't affect the input image, because this is a deep copy. And what that means is that every single list inside of this list of lists is a copy of the original. It doesn't point to the same list, so modifying things in output image doesn't modify things in the original input image matrix. That's as much as I want to say for this problem. I know you guys can do this. This is one approach that I'm proposing. There's lots of different ways to do this and to approach this. And so whatever you think you like, whatever approach you like, is what you should try to do. You could go ahead and handle each of these edge cases individually. But for this particular problem, you're going to need to think in terms of indices and not in terms of like the actual pixel list. For the previous problems, you might have you might have iterated through each row, and then for each pixel in the row, you did something. Here, you really have to think in terms of the R index and the C index, because you have to add up the pixels around the pixel that you're looking at. And to do that, you have to know the index of your current pixel to be able to get the pixel above, below, left, right, and the corners. Best of luck, and please ask away on Piazza if you have any questions. Bye.